Electric potential energy. Let's start with two positive charges initially at rest with Q at the origin. This plus Q right here is the origin. And this little q at infinity. In order to move little q towards big Q, a force opposite to the Coulomb repulsive force, remember, like terms repel, needs to be applied. If you don't have an external force, this q is never going to get there. So here we have Coulombs Law, which is K times big Q, little q, over R squared. And do you remember what this is from the last chapter? This is called R hat. It is a unit vector. Its magnitude is 1, and it's in the direction between these two charges in a straight line. So when we look at Coulombs Law, we see that the force is constantly changing as Q gets closer to big Q, because it depends on the distance r, and r is decreasing. So the force is constantly changing and increasing as we push Q towards big Q. Recall that work is defined as the force applied times the distance that it moves, only in the parallel direction. There's going to be two different kinds of work done. One, we're going to be pushing this with an external force, because if not, this charge will repel it. There's no way little q will get close to there. So there's going to be an equal and opposite force from this charge. Now the forces are equal and opposite because we want the net force on this charge to be 0. We want it to move at a constant velocity. So the kinetic energy never changes. So the only thing that's going to change is potential energy. This is not just a simple F times R problem though, because force continues to change with the distance. So we're going to have to use calculus. We'll save that for next year for APC. But once we get the work, we can find the potential energy is the negative of work. Now which work do we want to use? The work done by the external force or the work done by the field due to this charge? Well, we're going to use the work done by the electric field of the big charge, because then when we take the negative work of that, we will get the potential energy function. This is the same thing we did when we described gravitational potential energy, so you might want to review that. We're going to make an assumption that the potential energy of this system is 0 at infinity, which is where we're starting this guy from. We do that so when we talk about delta U, the change in potential energy, which is the negative of the work, since the potential energy out here is defined to be 0, we can just deal with potential energy. We can assign a potential energy to this system. So again, we would use integral calculus, and we'll find that electric potential energy is K times the two charges divided by R. And this here is a reminder that the two forces are equal, so that we do not have a change in kinetic energy. The object, the charge, moves at a constant velocity. The equation for the potential energy due to two point charges here, is potential energy K big Q little q divided by R. U is commonly used for potential energy. So for example, gravitational potential energy could also be written as U sub G. The benefit of using potential energy instead of force in fields, energy is a scalar. Calculations will be much simpler. There is no direction, but the sign does matter. We can have plus potential energy or negative potential energy. That is not implying a direction. It's just kind of telling you where on the number line of values you are. Just like gravitational potential energy, electric potential energy requires a system. It is not a property of just one object. In this case, we have a system of two charges, big Q and little q. There's another way to define the system. We can assume that the magnitude of Q is very much greater than the magnitude of little q. So the electric field generated by big Q is also much greater than the field generated by little q. Think of little q as a positive test charge, so we'll ignore that. We can look at this as a field charge system. And the electric potential energy will be a measure of the interaction between the field generated by the big charge Q and the little charge q. What is electric potential energy in words? It tells you how much energy is stored when you do work on the system, and this system now is able to return that energy in a different form, such as kinetic energy. Once again, just like gravitational potential energy. For example, if you put two positive charges next to each other, they are a system, and they will have electric potential energy. Once you release them, they will accelerate away from each other, turning potential energy into kinetic energy. These moving charges can now perform work on another system. It's a little tricky keeping track of the signs when we deal with potential energy, so let's show a few examples. A positive charge and a negative charge will have a negative potential energy of the system. You can just use the equation here, plug in the values, and see that you get a negative potential energy. But what does that mean? Well, let's look at the work being done by the electric field. The electric field force, due to a positive charge here, on a negative charge is going to be in this direction. Okay, so that is doing positive work because the charge is moving this way. So that means the potential energy decreases as the charges get closer to each other. That's your negative sign here. What are the forces acting? Well, we told you we wanted to keep a constant velocity, so that means the net force has to be 0. So the external force, right, so the balance of the forces here is 0. This is the force due to the field, force due to E field. Okay, so we have negative work being done by the external force to keep them from accelerating towards each other. The potential energy of this system decreases as the charges move closer to each other. What's the electric potential energy of like charges? So here we have two positive charges, here we have two negative. We want to bring, let's just work the top one, same thing applies here. We want to bring this charge in from infinity to meet this bigger charge. The electric field force is going to be in this direction. It's going to oppose it because they repel. So we're just going to put F electric field. To get these charges to move close to each other, we have to apply an external force in this direction. Force external. Okay. And once we get it moving, we want these two forces to balance, so we have a constant velocity, so the only change in energy will be potential. So what's happening here? What's the work done by the field? The work will be negative. The force is in this direction, the charge is moving this way. So if the work is negative, the potential energy must be positive. It must increase. So what we have, the potential energy of the system increases as the charges move towards each other, and that's represented by the positive potential energy.